All right, for paper 3, one of the smaller topics that we need to make sure that we're aware of is this thing called upper and lower sums, partial sums. And essentially what it comes from is situations where we have to integrate things that can't be integrated using traditional methods. So for starters, the problem as we define it is here, where it just says, here, let me go back a little bit. Find the upper and lower sums to estimate this integral. And we're trying to go from 1 to infinity of e to the negative x squared dx. This is the basis for the bell curve, by the way. Incidentally, I see this portion of the graph when x equals 1 is right here, and we go off to infinity. So this is one of those that appears as though there will be a finite area in spite of the fact that this goes on forever. Because I can't integrate this using traditional methods, what I can do is use upper and lower sums. And what that means essentially is this integral is the sum of infinitely narrow rectangles. But before we did that, we used to make larger rectangles and use those to approximate the areas. So we're going to start with the upper sums, that is the larger numbers, and we're going to start with k equals 1. And make a little rectangle that's 1 wide and as tall as the function at 1. So here's the 1 circled. So the next rectangle will be right here, which again we put in 2 for x, we go up to the function, we make a rectangle, and we calculate its area. And then I can't zoom in, but here we have where we could take x equals 3, go up to the graph, make a little rectangle, and calculate its area, and do that forever, ever, amen. The way to express that as a sum is to write this. The sum as k goes from 1 to infinity of e to the negative, don't forget this is k now, because we've replaced it from function into a series. And this is now k squared. But we know that if we add up all the rectangles from k equals 1 to infinity underneath this function, we are definitely going to be overestimating the area. So we know that's going to be greater than our integral. On the lower end, we're going to move the rectangles 1 unit over. So now we're going to start at 2, and we get a rectangle, and we start at 3, we get another rectangle, and so on. That's clearly going to give us a smaller area. We're going to be less than the integral from 1 to infinity. So that statement is set over here. Instead of going from 1 to infinity of e to the negative k plus 2, we're going to go to k equals 2. So that's 1 more than over on this side, and that's going to represent our lower boundary. So this is the upper sum, and this is the lower sum as boundaries. So if I could figure out a way to calculate this sum and this sum, then I would be able to eventually get a good approximation for the value of this integral. Be careful when finding upper and lower sums, because what's bigger and what's smaller is going to change if the function we're studying is below the x-axis. So here's an example of such a situation. When I write the integral and then I try to compare it to sums of rectangles, first thing I want us to notice is this function has been really zoomed in. This is negative 1/10 right here. Most of the values of the function are very close to 0, but they're all negative. And if I actually start with x equals, and I got to make sure, or k equals, I got to make sure I realize I'm going from 0 to infinity, not 1 to infinity. But when k equals 0, that produces these series of rectangles. Here's k equals 0, k equals 1, here's the k equals 2 rectangle, and so on. Now we can see that there's more area coverage here. We're going with a larger space. But because it's more negative, we're expecting the value to be less than the value of the integral. So the integral is going to cover less space, so it'll be a smaller negative number, therefore larger in absolute value, or larger in value. So when we do our other sums, when we go from k equals 1 to infinity, we're seeing these rectangles here are all negative, but it's going to be less negative than our integral. And so the work is inverted compared to what we did last time. So that's basically upper and lower sums. Essentially all we have to do is estimate our integral, and we're going to have a boundary on the right hand side, which would basically be k equals 1 or you'll see the general form in just a moment. We'll move on to that. Here's an IB style question that would utilize upper and lower sums. It starts off with the same question: find the upper and lower sums of the integral 10 to infinity of 2 to the negative x dx. So the first thing I do is, graphically speaking, I start at 10, I make my rectangles, and I realize that that's going to overestimate my area, so I put that on the larger side. And then when I start from 11, which is one more, I add up all the little rectangles, and I'm going to expect that to be smaller than the total area because I'm underestimating. As a result, we can look at this and realize this is actually a geometric series, and this is a geometric series as well. So the follow-up question would be, find the constants a and b such that a is less than the integral, which is less than b. So in other words, we should evaluate both of these summations on either end, and we will have the boundaries that will confine this integral within certain parameters. To do so, I can notice that the blue represents a geometric series, and the sum of an infinite geometric series is the first term divided by 1 minus the common ratio. Common ratio here is going to be 1/2, because 2 to the negative k is a half times a half times a half, k times. So the total sum is going to be 2 to the negative 11 divided by 1 minus a half, which is 2 to the negative 10. 2 to the negative 10 will be the sum of all of these fractions added up from 11 to infinity. Using similar reasoning, I find that the upper bound is 2 to the negative 9. So 2 to the negative 9, or 1 over 2 to the 9th, and 1 over 2 to the 10th represent the boundaries that confine my integral. So now, using the results that we found from part B, along with a little quick shortcut on how to integrate exponential functions not in base e, we need to show that 1/2 is equal to the natural log of 2 is less than 1. Now, a lot of people tend to start with the thing you're trying to show. I disagree. I think we should start with what we know. Here's something we know, and here I have the result from B. That's what I'm going to focus on. Here's a generalization of my result from B. If we're going to integrate from 0 to infinity, we are basically going to bound that between 1 over 2 to the 0 and 1 over 2 to the negative 1. That's what I got from my result from B, because here we had, starting at 10 to infinity, the right-hand side is going to be 1 over 10 minus 1, and the left-hand side is going to be 1 over 2 to the 10. So here we start at 0. That means our left-hand bound is going to be 1 over 2 to the 0, and this one's going to be 1 over 2 to the negative 1. So this is the basis for my proof. I see that the natural log is going to come into play, the natural log of 2 there. I see right here I have a 1/2, and I see right here I'm going to have something else. Well, we'll just see. This one actually turns out to be 1, and this one turns out to be 2. But let's have a little faith and see how this pans out. First thing I notice is I have an indefinite integral, and so I need to make a limit argument. So we make a boundary to b, and then we allow b to go to infinity, and that'll give us our infinite limit if it's possible. So to integrate 2 to the negative x, I get negative 2 to the negative x divided by the natural log of 2. We go from 0 to b, evaluate that integral for 0 and for b, and now we're going to let b approach infinity. Now if we do that, we're going to get 2 to the b, and b gets to infinity, so the denominator is going to get huge, which means the whole fraction is going to get closer and closer to 0. So my limit is 1 over the natural log of 2. Then what I did was, you can actually reverse the limit, the inequalities, if you take the reciprocal of everything. So the reciprocal of 1 is 1 over 1, the reciprocal of 1 over natural log of 2 is natural log of 2, and the reciprocal of 2 is 1/2. One step away from the thing I'm trying to show. Just reverse the inequalities, and you have it. So that's an example of how we would use upper and lower sums, why they exist in the first place. Also a very IB style question. What you can do now, if you like, is take a screen capture of this slide. If you screen capture this, you can practice finding upper and lower sums. And here's another screen capture. We'll give you some more, slightly more challenging exercises to explore. Have a good day.